In this video, we'll introduce the key components of a Wi-Fi network. A Wi-Fi network, also known as Wireless Local Area Network or WLAN, consists of the following key components. The access points, or APs, broadcast Wi-Fi signals, allowing your devices to communicate wirelessly. The access points are wired to the distribution system, or DS, which is the backstage area, where all the cables connect to the broader network such as switches, routers, and servers. Devices that connect to Wi-Fi, such as laptops or industrial equipment, are officially called stations or STAs, but they are also commonly referred to as wireless clients. Each access point has a unique identifier called a Basic Service Set Identifier, BSSID, which is the MAC address of the specific radio interface in the access point. The Service Set Identifier, SSID, is the name of the specific Wi-Fi network. When you search for a Wi-Fi network, you see a list of the SSIDs. Each network has its own unique SSID. When a device moves, it can go out of range of one access point and into the range of another. This process is called roaming. As the device connects to a new access point, the BSSID changes because each access point has a unique BSSID. However, since the network name doesn't change, the SSID remains the same. In this video, we'll introduce the different Wi-Fi generations. When discussing Wi-Fi technology, it's important to mention two key organizations. The Institute of Electrical and Electronics Engineers, IEEE, defines the technical standards for Wi-Fi, whereas the Wi-Fi Alliance ensures interoperability and certifies Wi-Fi products. A Wi-Fi certified product guarantees compatibility with other certified devices. In contrast, non-compliant hardware, often referred to as WLAN, does not guarantee compatibility. The first standard for wireless networking, or WLAN, was released in 1997 and called IEEE 802.11. It had the limited bandwidth of 2 megabits per second. A couple of years later, the next generations were released and called 802.11, B and A. These were later followed by versions called G, N, AC, and AX. As this was starting to get confusing, the Wi-Fi Alliance introduced a new naming convention in 2018. The different generations were called Wi-Fi 4, 5, or 6. For example, this allows consumers to easily identify if a product is Wi-Fi 5 capable rather than having to understand what 802.11ac means. Wi-Fi 6 also exists as an extended version called Wi-Fi 6E, with the added capability to operate in the 6 GHz frequency range. In this video, you'll get an overview of Wi-Fi communication and the currently available frequency bands. Wi-Fi operates on unlicensed ISM bands. Here's an overview of the 3 bands for Wi-Fi 4, 5, 6, and 6E. The 2.4 GHz band is widely used due to its compatibility with almost all Wi-Fi devices. It provides good range due to its lower frequency and longer wavelengths. However, this band is also used by other technologies and devices, which can cause interference. The 5 GHz band is less congested than the 2.4 band. Its higher frequency results in reduced range and makes it more prone to interference from walls and other obstructions. The 6 GHz band is the latest addition to Wi-Fi frequency bands. It offers many channels, allowing it to handle more traffic at higher speeds. Although it's not yet available in all countries, its adoption will bring faster and more reliable Wi-Fi. Before going into the specific channels of each frequency band, let's first take a look at how communication over Wi-Fi channels works. Each device connected to the same access point is in the same collision domain. These devices listen to each other and take turns using the radio spectrum. If the channel is busy, a device waits for a random period of time before rechecking the channel. Essentially, devices compete for airtime. This process is called Carrier Sense Multiple Access with Collision Avoidance, or CSMACA. Note the difference to cellular wireless technology, where the operator or core network will determine which device that is allowed to send. Since Wi-Fi devices transmit in turns based on channel availability, proper channel allocation is crucial when configuring Wi-Fi access points. To achieve optimal channel allocation, a basic understanding of the channels in each ISM band is necessary. Let's first look at the channels in the 2.4 GHz band. There are 14 channels, of which 11 are available worldwide. Each channel is separated by 5 MHz. If each channel would be used by Wi-Fi with the bandwidth of 20 MHz, overlap and interference would occur. To prevent interference, it's recommended to use only channels 1, 6, and 11, as the distance between these channels is sufficient to prevent any possible overlaps. Using automatic settings often results in other channels being selected, which can lead to overlap and interference. Therefore, it's recommended to turn off automatic settings. The 5 GHz frequency band spans from about 5.2 to 5.9 GHz and offers more channels, none of which overlap. The 5 and 6 GHz bands are divided into unibands, which stands for Unlicensed National Information Infrastructure. The uniband 1 can be used worldwide without restrictions. Other unibands may come with regional restrictions, for example, to avoid interference with radars. Since the 5 GHz band has more channels than the 2.4 GHz band, it allows for the use of wider frequency bands used for transmitting signals, which can support higher data rates. For example, while 20 MHz is common in the 2.4 GHz frequency, 40, 80, or 160 MHz can be used in the 5 GHz band. This is one of the reasons why the 5 GHz band is often preferred for applications requiring higher data rate. The 6 GHz frequency band spans from 5.9 to 7.1 GHz and provides even more non-overlapping channels. This allows for wider channels for high data transfer. However, it's important to note that availability worldwide is currently limited. In this video, we'll introduce some of the key points to consider when designing a Wi-Fi network. In the early days of wireless networking, Wi-Fi networks were often designed for extensive coverage, sometimes at the expense of capacity. Main reason for this was that there were fewer wireless devices in use. However, focusing on large coverage can be problematic, as range and data rate are inversely related. When a device is far from the access point, data transfer takes longer, which can potentially slow down the entire network. Devices closer to the access point must wait their turn to transmit data. Nowadays, setting up a Wi-Fi network requires balancing both coverage and capacity. Capacity refers to the number of devices supported at the same time, considering factors like applications, bandwidth consumption, and available Wi-Fi access points. It measures how many users can use the network simultaneously and at what speed. Balancing coverage and capacity ensures efficient data transmission across the network. When planning the placement of access points, it's important to consider walls and other obstacles, as they affect both coverage and capacity. It's best practice to use site surveys both before and after the installation. A predictive site survey is a simulation which helps determine the number of access points needed and their optimal placement. An on-site survey then validates the installation and allows you to make any necessary changes. The on-site survey is also a useful tool to troubleshoot any future issues. Let's examine a real example where a site survey was used to troubleshoot Wi-Fi issues. A rubber manufacturing plant experienced problems with its Wi-Fi network. When looking only at the signal strength, where green indicates a good signal and red indicates no signal, everything appeared fine. However, this view misses the background interference. To the right, you see the view of the signal-to-interference ratio. In the large red area, a machine utilizing microwave technology to vulcanize rubber was in operation. Since the machine's microwaves operates at 2.4 GHz, the same frequency as the Wi-Fi, the interference here was too high. Unlike Wi-Fi, the machine does not take turns transmitting signals. Instead, it continuously transmits, leading to constant interference. This high interference is also visualized in the spectrum analysis at 2.4 GHz, showing the access points signals on channel 1, 6, and 11. You can see that the signal strength of the machine was higher than that of the access points. This high background interference prevented any Wi-Fi signals from getting through. So what was the solution? Since there was too much interference on the 2.4 GHz band, the rubber manufacturing plant decided to switch the Wi-Fi to the 5 GHz band, where there was much less interference. To conclude, coverage, data speed, and potentially interfering objects must be taken in consideration when designing your Wi-Fi network. A good way to identify and resolve issues is by conducting both a predictive and on-site survey. In this video, we'll present 3 Wi-Fi use cases. Firstly, in this manufacturing plant, the equipment is spread out in various locations. In a traditional setup, accessing, for example, a PLC within a control cabinet requires a physical cable connection. Technicians must be physically present at the control cabinet, which can be difficult to access or pose a safety risk. Additionally, it might be required to shut down the equipment to connect the cable, resulting in unwanted downtime. With Wi-Fi, technicians can access equipment such as a PLC or a robot wirelessly, eliminating production halts and safety compromises. They can monitor and control the equipment, all from a safe distance. This leads to a boost in productivity and ensures a safer work environment. Wi-Fi has become the main method for accessing equipment wirelessly, as it provides sufficient bandwidth for a remote HMI. By accessing the machine data easily, the manufacturing plant will benefit from increased operational efficiency and simplified maintenance procedures. Next, within an electronics factory, automated guided vehicles, or AGVs, transport materials from one station to another. This ensures a smooth flow of parts, keeping the assembly line efficient. Any delay in material delivery can cause significant slowdowns and needs to be avoided. Due to the machine's mobile nature, wireless technology is essential for communication with other factory systems, such as fleet managers or safety protocols. Using Wi-Fi or cellular technology such as 5G enables the AGVs to receive updated information and instructions wirelessly. This connectivity enables dynamic routing and scheduling, allowing AGVs to quickly adapt to production changes or obstacles by rerouting to avoid congested areas and prioritizing urgent deliveries. In addition, wireless technologies enable centralized control of the AGVs, allowing fleet managers to optimize workflow from a control room. This enhances transport efficiency and provides data for ongoing process improvement. Finally, a critical aspect for AGVs as well as for autonomous mobile robots, AMRs, is safety over wireless. The EU Machinery Regulation from 2023 classifies AGVs and AMRs as machines, not vehicles, as they were previously. All machinery must meet health and safety requirements to minimize accidents and ensure safe operation. This includes an emergency stop that can be activated remotely. To date, Wi-Fi is the standard choice for AGV installations. However, for applications with high demands on safety, low latency, and security, 5G is becoming a more viable choice.